Good afternoon, and welcome to this special astrophysics colloquium by Professor Walter Lewin. The mission of MIT is to advance knowledge and educate students in science, technology, and other areas of scholarship that will best serve the nation and the world in the 21st century. Few people can embody that mission in one person. Walter Lewin is one of those very special people. Walter, of course, is the most famous physics lecturer that MIT has ever had. In addition, he is the father of much of contemporary X-ray astronomy, the study of exotic phenomena in accreting neutron stars and black holes. He received his PhD in 1965 from Delft University in the Netherlands, and at the beginning of the following year, he came to MIT as a postdoc in the lab of George Clark, and quickly became an assistant professor. He began studying the skies using balloons to carry aloft X-ray detectors to measure cosmic X-ray sources. The 1960s, as we will hear in this lecture, were a golden era for the discoveries made using new technologies in space and at the edge of space, the top of our atmosphere. In the 1970s, he played a key role in the SAS-3 satellite mission, including the discovery of the rapid burster, an amazing object which emits flashes of light of X-rays more than 5,000 per day. Nowadays, we talk about cosmic gamma ray bursts as being the fascinating phenomenon in the universe. But from the entire universe, we see perhaps one gamma ray burst per day. This object was emitting 5,000 X-ray bursts per day. In 1974, Professor Lewin became a full professor and continued his pioneering studies of cosmic X-ray sources, including in the 1980s the discovery and the study of quasi-periodic oscillations arising from the accretion disks of matter swirling in the very strong gravitational fields of neutron stars and black holes. Indeed, he became one of the experts in applying these measurements to testing general relativity in the strong fields produced in those objects. In more recent years, Professor Lewin has become famous for his physics lecturing. Many of you have seen his lectures. Perhaps some of you were fortunate enough to attend the special lectures he gave this summer for Japanese television on his physics, electromagnetism, classical mechanics, and waves, the beauty of music, the beauty of a rainbow. In fact, I would expect that many of you have read his book, For the Love of Physics. If not, please do. I've read it from cover to cover, and as he says in his lectures and in the book, it will change your life forever. He's received many awards for both his scientific research and his teaching contributions, including the NASA Award for Exceptional Scientific Achievement, the Buckner Teaching Prize of the Physics Department, the Baker Award of MIT, and many others, including last year being selected by Princeton Review as one of America's top 300 professors and the only one from MIT. Professor Lewin has been an inspiration to me personally as far as integrating teaching and research. He exemplifies the very best in everything he does. I know that for this one lecture today, he practiced 4 or 5 times, including at 6 a.m. this morning. So I hope that you are still full of energy, Walter, as always, and I look forward with the rest of the audience to your wonderful lecture to come. Please welcome Professor Walter Lewin.
I've been on many oral committees whereby we tested the students on their knowledge on astrophysics. And I typically would ask, what do you know about X-ray astronomy? Don't bother me with the sun. I want to hear about extrasolar X-ray astronomy in the range 1 to 10 keV. A student would say, well, there are about 100 very bright X-ray sources in our galaxy. They're binary systems, many of them, with a neutron star and with a black hole. And there's mass transfer, and potential energy is converted to kinetic energy. It gets very hot, 10 to the 7 degrees, and you get X-rays. Quite impressive. But I say, tell me a little bit more about these binaries. Tell me are they variable in time? And then the student says, oh, you won't believe it. Millisecond timing, weeks, hours, years, anything has been observed. And he said, and the worst of all is, there are X-ray sources which pulsate. They have a period, rotating neutron star. Well, I was always very impressed, but I would go a little bit further, and I would say, how about galaxies? Are there any particularly bright X-ray galaxies? Student says, yeah, you better believe it, very bright ones. We give them a name, we call them AGNs, active galactic nuclei. Well, time was running out, but I still wanted to go a bit further. How about clusters of galaxies? What do you know about the clusters of galaxies? Students would say, well, that is a fantastic story, because there is hot gas which is trapped in the potential well of the cluster. Not well understood why, and that's 10 million degrees hot, and so that hot gas emits X-rays, and the mass of that hot gas is often much larger than the mass of the galaxies. Well, before I finish that exam, I would say, is there such a thing as a diffuse X-ray background? Like the 3-degree cosmic background radiation coming from all directions. And now the student begins to hesitate. Yeah, the student said, yeah, there is such a thing. I said, does it come from all directions? Yeah, he thinks it comes from all directions. I said, from how far does it come? Is it nearby or is it very far away? Clearly, the student doesn't know. But he did so well, he passed. Now, most of you probably knew all this. And if you didn't, then I would say try hold on to it for only 1 hour. And then you can forget about it again. And I want to talk today about how all this came about, how it was discovered, and I restrict myself to 10 years, the first 10 years of X-ray astronomy, 1962 to 1972. Edward Hurlbut suggested in 1938 that the E region of the Earth's ionosphere was partly caused by X-rays from the sun. And in 1948, attempts were made to detect the solar X-rays by Burnite and Tousley, and they used V2 rockets, which were developed in Hitler Germany by Werner von Braun. Werner von Braun used slave labor from concentration camps. 20,000 people died. Werner von Braun was a war criminal, but later in the United States, he became a hero. And that still puzzles me. Rockets were seized after the war, and both Burnite and Tousley believed that they had actually detected X-rays from the sun. But it was a little bit ambiguous because they had no directional information. In 1949, Herb Friedman of the Naval Research Laboratory conclusively demonstrated that the sun indeed emits X-rays. In the summer of 1959, Bruno Rossi, who was a professor at MIT, chaired meetings of the Space Science Board, and among the topics that were discussed was X-ray astronomy. And Bruno went to his ex-student, Martin Ennis, who was at that time the president of American Science and Engineering, was very close here in Cambridge. Bruno was the chair of the board. ASNE was involved in investigations of the effect of nuclear bomb explosions in the upper atmosphere. And Martin was very enthusiastic and willing to commit resources for X-ray astronomy. I'd like to show you a picture of Bruno. And you see Bruno Rossi here together with Beppo Occhialini, Italian. And what is so special about this picture, that both men got an X-ray observatory called after them. The Bruno Rossi Timing Explorer and the Beppo Sachs Observatory, which was the Italian one. Riccardo Giacconi had joined ASNE early in 1959, and in September that year, Bruno Rossi discussed with Riccardo to explore X-ray astronomy, and Riccardo picked up the ball and he ran with it. He explored various avenues into X-ray astronomy, and they first, together with Bruno Rossi, George Clark, and Stan Albert, all at MIT, they wrote a report in which they evaluated the possibility of X-ray sources. And they mentioned the Crab Nebula. That's a supernova remnant at a distance of 6,000 light years. And they also mentioned the moon. Nice and close. X-rays from the sun could be scattered off the moon. If you place the sun at a distance of 100 light years, there is no chance on Earth that you will be able to detect it in the early 60s with the available detectors. You were short by 8 orders of magnitude. So the odds were very, very small. So Riccardo explored the possibility of concentrating X-rays in order to get a higher sensitivity. And in 1960, he wrote a joint paper with Bruno Rossi in which they used parabolic mirrors, grazing incidence, X-ray optics in order to improve the sensitivity. And you see here the paper. The paraboloidal surfaces are here, and the idea of nesting them, more than one, was Bruno's idea. And so the X-rays come in, and here's grazing incidence, and here they come together, and that, of course, would enormously improve the sensitivity because you would have much lower background. Hans Walter had studied the problem of X-ray emission a decade earlier in an attempt to develop an X-ray microscope. In his case, the X-rays are reflected twice. Grazing incidence first of a paraboloidal mirror and then of a hyperboloidal surface. It was very unpractical for microscopes, but Riccardo recognized its usefulness for an X-ray telescope. And by 1965, he had built one, designed one, and tested one, and published one. Typical Riccardo. Riccardo also realized that it would take a long time for these mirrors to be built, and so he explored the possibility of developing large area Geiger-Müller counters. That was done at ASNE by Frank Paolini. They were supposed to be large, and they were going to have what's called an anti-coincidence shield. Bruno Rossi is the inventor of the anti-coincidence circuit. And what this anti-coincidence shield does is very important. It discriminates between X-rays and cosmic rays, so it keeps the background down. Proposal was sent to NASA. Turned down. Proposal was then sent to Air Force Cambridge Research Laboratory. And Riccardo made some changes in the proposal. He stressed the fluorescence of solar X-rays from the moon. I suspect that he suppressed the Crab Nebula as the Air Force may not have been too interested in something that is 6,000 light years away from us. But the moon is 1 light second. That's within striking distance. the proposal was approved. The first rocket flight was in June 1960. The rocket failed. A second rocket flight in October 1961, the doors of the rocket wouldn't open. And the successful flight came on June 18, 1962, from White Sands. Herb Gursky, who had joined ASNE a year earlier, was present during the launch. Ricardo was not, because Ricardo was involved in the bomb testing business of ASNE, so he was not present during that launch. They launched 1 minute before midnight on June 18. There were 3 large area Geiger-Müller counters on board. Large area in those days was the size of a credit card. So they had 3 Geiger-Müller tubes about this size. The rocket was 6 minutes above 80 kilometers. It had no collimation or whatsoever. So the field of view was 2 pi steradian, and the rocket would rotate 2 revolutions per second. And they detected a signal, loud and clear. But of course, at first, there was great concern. Were these really X-rays? So they scrutinized the result as much as they could. They tried to explain them away, but they did not succeed, and so they decided to publish. It was published in PhysRev Letters in December 62, and the title was Evidence for X-rays from Sources Outside the Solar System. And in that article, they mentioned that they also had discovered what they called diffuse X-ray background. That's the thing that the student had problems with. Diffuse X-ray background. The editor of PhysRev Letters was Goudsmit. And Goudsmit called Bruno one day, and he said to Bruno, "Do you really believe this? Do you really believe that this is an X-ray source outside the solar system?" And Bruno says, "I happen to be co-author on that paper." Goudsmit said, "Yeah, you're right. We'll publish it." I'll show you here a picture of Ricardo together with Herb Gursky. They were not yet at ASNE. This was in 1958. At that time, they were together in Princeton. And here then comes the most important paper ever written in X-ray extrasolar X-ray astronomy, which is that discovery paper. And if we look at this, then on the left here, you see the counting rate in X-rays, and this is 360 degrees in azimuth, so that's the whole horizon. And you see 2 curves. One detector failed, so that's why you see 2 curves. The curves are not identical because the thickness of the windows of the 2 counters was different. And there is just no question that there is at least one source here. And it is not the moon, because then the peak of the source would have been here. And this is what they called the diffuse background. In all directions where you looked, you would still see X-rays. This here is the entire sky above the horizon when they flew the detector. And they put the source in this error box, 10 by 10 degrees. That's the best they could do, which is an amazing thing if you have no collimation at all, a field of view which is as large as the sky, and you still make the commitment that the source would be located in a 10 by 10 degree area. What you never read in the literature, in not a single book, that they were off by 25 degrees. Because later it was found, and you will see why and how, that the source is here. When this was published, of course, it was an A-bomb explosion, and Herb Friedman at NRL immediately flew an X-ray detector in April '63, and he pinpointed the source and found that it was in the constellation Scorpio. The 10 by 10 degree box is so large that there are at least 2 stellar constellations, but maybe even 3 in the 10 by 10 degree box. Therefore, in that discovery paper, they could not identify the constellation. And the constellation is not identified in that paper. Even though Ricardo, in a book that he recently wrote, claims that they found the source in SCO X1, which is not true. So now comes the question, what are these objects? Are they optical counterparts? The X-ray luminosity must be phenomenal, but even if you put the source as close as 100 light years, which is next door, right, then they would be at least 8 orders of magnitude more powerful than the X-rays that are produced by the sun. So it has to be an object completely different from the sun. By 1964, about a dozen sources had been detected, and the groups that were active at that time were AS&E, Ricardo's group, Herb Friedman, NRL's group, Lockheed. Shortly after that, MIT followed. Hale Brott, Sal Rappaport, maybe in the audience, I know that Hale is. George Clark, I hope he is in the audience. And Jim Overbeck were active at MIT. And then there was Lawrence Radiation Laboratories in Livermore. In 1964 came the first optical identification with an X-ray source, and that was the Crab Nebula. There was already a source known that was called Taurus X1, and everyone sort of suspected it might be the Crab. The Crab Nebula is a supernova remnant from the year 1054. And Herb Friedman realized that the moon was going to occult the Crab Nebula. And he timed several rockets in a row that he launched when the moon was going over the Crab Nebula. And he reasoned, if the Crab Nebula is the source of X-rays, the X-rays will disappear during the flight. An incredible idea, and Herb was right. It was the Crab Nebula. You see at the top the Crab Nebula. It's about 6 arc minutes in the sky. From here to here, it's a supernova remnant. You see the rim of the moon here. And what you see here is the counting rate in X-rays. And this is 400 seconds, what was the duration of the rocket flights. He used more than one rocket. And here you see the counting rate very slowly going down as the moon comes over the Crab Nebula. So that was a source of X-rays that had a huge size of several arc minutes. In 1966, Phil Fisher, published a paper in which he compared the flux, the X-ray flux of 7 sources. Some had been seen by Lockheed and some by NRL, and he compared the intensities of the 2 different observations from the 2 groups with the same source. And if you look at that, and I will show you a slide of it now. May I have my first slide? Now, if I were you, I would say, well, could Walter, for this particular colloquium, not prepare a better slide than this one? And the answer is, yet he could have, but he didn't want to. Because this is the first slide that I made when in January 1966, I came here to MIT. I made this slide myself. It's 47 years old. And if you don't like it, tough luck. What you see here, though, which is important, you see here the observations of these sources by one group, and here you see the observations by the other group. This is the number of counts per square centimeter per second, one group, the other group, and here you see the ratio between these two, and then you see thickness x1, you see 0.2. Well, if that's not variability, you wonder what is. But Fisher did not say thickness x1 is variable. You must understand, in these early days, there was no believable intercalibration between instruments of one group and the other group. And in fact, if you flew the rocket, your own rocket, twice in a row, you didn't even know whether it performed exactly the same way as it did before. So he writes the following, I quote him, "Because time variation in X-ray flux may someday be observed." He didn't claim it had been observed. "May someday be observed, it may be worth noting that the fluxes used for Table 4 were derived from 3 different rocket flights made over only a 5-month time interval." That's enough for this slide. 1966 brought the optical identification of SCO-X1. It was a collaboration between ASNE and MIT. Hale Brott was part of that collaboration, and they used a new kind of collimator which was invented by Minoru Ode, who was at MIT at that time. We call it the modulation collimator. It is an instrument with a large field of view of several square degrees, but an intrinsic capability of angular resolution of arc minutes, or even better. It's interesting that when you go to Japan, they call it the Ode collimator. It was flown, and the flight was successful. And immediately after the flight, because of the modulation pattern that they recorded, they knew that the source was smaller than 20 arc seconds. So way smaller than the Crab Nebula. Smaller than 20 arc seconds, well, the idea came up, maybe it's a star. It took longer to analyze the position of the source with the modulation collimator. So the first thing they saw immediately, that it was a size smaller than 20 arc seconds. And Yugaku and co-workers of Tokyo Astronomy Observatory started to search the sky over several square degrees to search for a star that might be SCO-X1. And all they knew that might be a star, which could be wrong. And they said, they found one that they say, it's very bright in UV, 13th magnitude star, and they claimed that might be SCO-X1. Turned out later that they were right. The error boxes of the modulation collimator were worked out. Of course, it took a little longer. I want to show you the error boxes. And indeed, the Yukaku star was in one of them. First, what you see here are those hashed areas. Hey, oh. That's what happened on the second rocket flight, remember, in 1961. The window didn't open. You see here these hashed areas, which are error boxes that were obtained with rocket flights. I see here the name George Clark, so he must have been first author. This is one of his, and this is one of the rocket flights. This was a rocket flight, and this is 2 degrees, by the way, 2 by 2 degrees. And this whole area was searched by Yugaku. This whole area was searched to find SCO-X1. And then when the modulation collimator results were known, the source was found in this box, and the blow-up of this box is here, and you see a 1 by 2 arc minute error region and a 1 by 2 arc minute error region, and in this one was the Yugaku star. There was no doubt that the optical identification of SCO-X1 had been found. Now, once you know the optical identification, you know both the optical flux and you know the X-ray flux. You may not know the distance, but you know the ratio of the two, because they are at the same distance, of course. If we take the sun, and we take the X-ray luminosity, and we divide that by the optical luminosity, then even though it's highly variable, it's about 10 to the minus 6. Only 1 part in a million of the sun are X-rays. If you take SCO-X1, and you do the same, Lx over Lop, you find 10 to the third, 1,000. The difference between those numbers, 9 orders of magnitude. This is an object that emits optical light. Forget the X-rays. This is an object that emits X-rays. Forget the optical. 99.9% of all the energy that comes out of this source is in X-rays. So these sources are very, very special. And you can't even think of them as being sun-like. So the idea is, what are they? In April 1967, the Australians discovered a source which was almost as bright as SCO-X1, and they claimed that they looked at that source, at that region of the sky 4 months earlier, and they saw nothing. So they called this source an X-ray nova, not unreasonable name, and they were jubilant because it happened to be located in the constellation, the Southern Cross. Therefore, they called the source Crux X1. Why were they jubilant? They went bananas because the Southern Cross is in their flag. How tragic for them that when a more precise position became available, the source moved only 1 degree into the constellation of Centaurus. And so now we know this source as Cenex-2. I remember shortly after this was published, I was on the phone with Herb Gursky, and Herb said to me, "Walter, do you believe this nonsense?" And that is so typical for those days. It wasn't believable that there was a source as bright as SCO-X1 one day and 4 months earlier there wasn't. Herb said, "Oh, of course, the first time the detectors didn't work." Do you believe that nonsense? Well, the source was there. And not only was the source there, but it was observed by various groups, and the source gradually in time faded. What you see here is 2 years of data. This is the X-ray intensity. These are 3 decades, so this is a logarithmic scale. And this was the time that the observation showed no source at all. And then here is the first observation on April 4, 1967. And then other groups came and other groups followed it, and then the source gradually decayed away. By the way, we no longer call these sources novae. We call them now X-ray transients. In 1967, Herb Friedman wrote a paper with 30 sources, and he compared them, and these observations had been made over a period of about 2 years. And if you compared the observations of the same source, months and years apart, there was clearly variability. The most noticeable was actually Cygnus X1. But again, no one had ever seen a source change its flux while you were looking at the source. And why was that impossible? Because a rocket was only 5 minutes above the atmosphere. You don't have very much time in 5 minutes. Even if you were to look at one source, you may not see variability, but of course they scanned the sky in those 5 minutes. They wanted to see many sources. On October 15, 1967, SCO-X-1 was caught with a smoking gun. George Clark and I had a 7-hour balloon flight from Australia, and we observed that SCO-X-1, during our observations, while we were looking at it, went up by a factor of 4 in 10 minutes. Rockets could never have discovered that. I'd like to show you the data. Horizontal scale is time. And from here to here is 4 hours of data. Balloons could fly 10 hours. I once had 26-hour balloon flight. That was a great advantage of the balloons. Each data point is an observation of SCO-X-1. We did see it here, although the error bars are large. But near the end of the flight, it was unmistakable that SCO became bright. In 10 minutes, it was flaring up, and then it went down again. So we submitted the paper to Astrophysical Journal Letters. Chandra Sekar was the editor. And we got a referee report back. And the referee report said, this must be nonsense, because we all know that sources so bright could never change by a factor of 4 in 10 minutes. You wonder what he meant when he said, we all know. So we wrote a note to Chandra Sekar and we said, well, we're sorry, but we stand behind our data. Chandra Sekar called Bruno. And Bruno must have said a few nice things about George and me, because the paper was accepted. And that was the first time that the variability was observed while the source was observed. Radio pulsars, with a period of about 1.3 seconds, were discovered in 1967 by Jocelyn Bell and Anthony Hewish. Anthony got the Nobel Prize for that in 1974, and Jocelyn did not share the Nobel Prize. That was a scandal, a blunder of astronomical proportions made by Stockholm. I've talked about this many times. I will leave it with this, but you should remember that she should have shared in the Nobel Prize and did not. Shortly after their report of these radio pulsars, Dave Stalin at MIT looked at the Crab Nebula, and he found the pulsar in the Crab Nebula, and the period of that pulsar was 33 milliseconds. So it was believed by that time already that the period was the result of rotating neutron stars. And so the 33 milliseconds meant that you had a neutron star that rotates around 30 times per second. It was in February '69, when I was preparing for new balloon observations, that Jeffrey Burbidge visited MIT. And I had lunch with Jeffrey. Many of you have known Jeffrey. He had a wonderful, deep voice. He laughed a lot, and when Jeffrey laughed, the ceiling was moving. So I had lunch with him, and I said, Jeffrey, I was wondering, the time resolution of our telescope, of which George Ricker was part, was only a few seconds. And don't you think it may be a good idea, now that we know there are 33 millisecond pulsar in the Crab, shouldn't we change the time resolution to milliseconds? And Jeffrey started to laugh. We were in a restaurant and people were looking around. And Jeffrey said, Walter, you will see no X-rays from any radio pulsar. You don't understand anything about pulsars. Well, he was right. But he didn't either. Because very shortly after that, Herb Friedman and independently Hale Brott discovered the 33 milliseconds in X-rays. In the years 1970 to 72, my balloon group, of which George Ricker was part, discovered sources that had never been seen with rockets. And the reason for that was that we had so much more observing time. These sources were very faint, very high energies. Rockets didn't stand a prayer. We discovered 301-2, we discovered 304-1, and the most important that we discovered was GX1 plus 4, because we noticed and reported that it was periodic with a period of about 2.3 minutes. At the time, we had no idea what that meant. Now we do, but it was the first source with a periodicity that long, 2.3 minutes. What are these sources? We knew the Crab Nebulae. We knew that the luminosities in X-rays must have been horrendous. There were many sources known by that time, and the majority were in the galactic equator, so you can estimate statistically the distance, which is about the distance to the galactic center, must be approximately right, which is 25,000 light years. And so the X-ray luminosities of most of these sources was of the order of 10 to the 37 ergs per second, which is 10 orders of magnitude higher than the X-ray luminosity of the sun. 10 orders of magnitude higher. As I said earlier to you, the object couldn't be anything like the sun. Between 64 and 66, papers were published by Ed Salpeter and by Hayakawa and by Zeldovich, in which they mentioned the possibility that a supermassive black hole was accreting matter, not a binary system. We call that Bondi accretion. And that the gravitational potential energy converted to speed, kinetic energy, and that might actually produce the X-rays. In 1967, Slosky wrote a paper in which he tried to explain SCOX1. So this paper was only about SCOX1. And he said SCOX1 is a binary system. There is a nuclear burning star, and there is a neutron star, and there is transfer of mass from the nuclear burning star to the neutron star, and there is a huge amount of gravitational potential energy converted to kinetic energy. When it hits the neutron star, it gets so hot you get X-rays. And that was exactly right. And I will quote from that historic paper. And the strange thing is, I read that paper at the time. We didn't pay much attention to it. But I quote from Slosky: by all its characteristics, this model corresponds to a neutron star in a state of accretion. The natural and very efficient supply of gas for such an accretion is a stream of gas which flows from a secondary component of a closed binary system towards the primary component, which is a neutron star. I'll show you now a slide which is sort of the idea that he had. Okay, so the basic idea is here is a nuclear burning star and here is a neutron star. Forget for now this disk, that's not important for now. And these two stars are so close together that it is energetically more favorable for the matter to go to the neutron star than to stay here. And so as it starts falling and falling and falling and falling towards the neutron star, picks up speed and speed and speed, so gravitational potential energy is converted to kinetic energy, and that means heat, and if the temperature is high enough, then you get X-rays. Now you can see why comparing it with the sun is an absurdity. If you compare these sources with the sun, you're comparing apples and coconuts, because the sun is a single object. But here, you see, this is the sun, so to speak. Here, this is the object that radiates the optical light, and this is the neutron star from where the X-rays come. And that can therefore also, in a very natural way, explain this crazy ratio that I wrote on the blackboard. Yeah, you can make it lighter again. We don't need this slide anymore. In 1966, the group at NRL, Herb Friedman, published the first X-ray detection from a galaxy in the Virgo cluster, which is 60 million light years away from us. They suspected that it was M87 because that's the brightest galaxy in this cluster, and that's what later was called an AGN. Remember? The student remembered that, active galactic nucleus. And the luminosity was 10 to the 43 ergs per second, which is equivalent to 1 million bright X-ray sources in our own galaxy. The first X-ray observatory, Uhuru, was launched on December 12, 1970, off the coast of Kenya. It was on Independence Day, and the Swahili word for independence is Uhuru. It was an all-American science observatory, and Ricardo Giacconi was the PI. Uhuru had 2 collimators, 1/2 degree by 5 degrees, and 5 by 5 degrees, and it rotated around once in 11 minutes. In 1971, they published a paper, Minoru Oda was first author, in which they said it is very probable that Cygnus X1 is a 73 millisecond pulsar. This was a courageous statement because the time resolution of Uhuru was 100 milliseconds. And if you want to claim that you see a periodicity of 73 milliseconds and your time resolution is 100 milliseconds, nature doesn't work that way. And so it's not surprising that the claim was wrong. But Ricardo told me later, and I believe him, that this result, even though it was not correct, accelerated the search for pulsars in Uhuru. And shortly after that, in May 1971, they found 4.8 second pulsations from a source, SENX3. However, there was no observational evidence that there was a binary system. And to make it worse, the 4.8 second pulsations were not constant. On day 1, they were different from day 2 and day 3. And that argues against the neutron star, because obviously neutron stars cannot possibly change their rotation period on such a short timescale. X-ray astronomy was flourishing and dominated all of astronomy. That is no exaggeration. I went to the library this morning and I picked a random APJ letters, Astrophysical Journal letters. I picked a random one from August 1971, and I want to show you the cover page. And I don't want you to read all those names because that's not my objection. Now, there's something with the light wrong because we can't see this anymore. Oh, this has to warm up. All right, then we let it warm up. I would like, it's getting better. Probably conversion from gravitational potential energy to kinetic energy. So yes, there are names here of people who are in the audience. There are people who were at MIT who are here. That's not why I'm showing this to you. I want you to see how X-ray astronomy took over the field of astronomy. Read the titles: X-ray observations of Virgo XR1, X-rays from the Magellanic Clouds, measurement of the location of the X-ray source Cygnus X1. X-ray source positions for Cygnus X1, Cygnus X2, and Cygnus X3. On the location of Cygnus X1, radio emission from X-ray sources, X-ray observations of GX17 plus 2 from Uhuru. And then a search for deuterium on Venus. How bizarre. Chandra Sekhar, who was the editor, must have had a very weak moment. The breakthrough came from optical astronomers, two independent groups, Webster and Murdin and Tom Bolton. They observed the most likely optical identification of Cygnus X1, and they discovered that it was a binary system with an orbital period of 5.6 days. But in addition, they measured the Doppler shift of the star that they saw. These stars have spectra, and these spectra have absorption lines, dark lines in the spectrum. And when the star is in a binary system, if the star comes to you, the absorption lines are shifted towards the blue. We call that blue shift. If the star goes away from you, the absorption lines move to the red. We call that red shift. And those curves are called radial velocity curves. And they measured the radial velocity curve of the optical component of Cygnus X1, and they knew it was a binary. Once you have that radial velocity curve, you see immediately the period, and you also get information about the speed of the star, because it's Doppler shift after all, so you get information about the velocity. And if you know your high school physics and you add Kepler's laws, to make a long story short, you can then find a lower limit to the mass of the other source, which in this case would be the accretor, the X-ray source. And this mass that they found was larger than twice the mass of the sun. As you all know, a white dwarf cannot be more massive than 1.4 the mass of the sun. We believe that neutron stars can really not be much more massive than twice, maybe 2.5 times the mass of the sun, because then they become black holes. Webster and Murdin published their data on January 7, 1972. And I will quote from Tom Bolton's paper. The high energies of the X-rays imply that large accelerations are involved. Accelerations such as might be produced by the intense gravitational field of a collapsed object. The lower limits placed on the secondary mass are too high for a white dwarf and probably rule out a neutron star. This raises the distinct possibility that the secondary is a black hole. These guys discovered, number one, that these X-ray sources were X-ray binaries, and the very first one, that the accretor was a black hole. I'd like to show you the radial velocity curve because of its historic importance. It's a Doppler shift curve. If the source is coming to you, then you have the higher velocity of the lines, so you're here. If the source goes away from you, you're here. And, of course, the time from here to here is exactly the orbital period, which is the 5.6 days. So with this data alone, and with a little bit more, you can get the lower limit of the mass of the accretor. And that's an incredible accomplishment. The popular press and even the professional literature almost never mentions this milestone discovery. They credit Uhuru with the discovery of the binary nature of X-ray sources, And most also credit Uhuru with the discovery of the black hole in Cygnus X1. Both is incorrect. Uhuru did not discover X-ray binaries, did not discover that the accretor in Cygnus X1 was a black hole. The reason why people have it wrong is that only a few weeks later, after the publication from Webster and Murdin, Uhuru group showed that Cenex 3 is a binary system, orbital period 2.1 days, 4.8 second pulsations, a rotating neutron star. The 4.8 seconds showed Doppler shift, 2.1 day Doppler shift. So the 4.8 second period was not constant. That's why a year earlier they were so surprised that the 4.8 seconds changed all the time. Well, that was the Doppler shift in orbit. And they even saw X-ray eclipses. That means that the neutron star was hiding behind the donor star, and then the X-rays are blocked out. And that was so overwhelming. That was everything that you could hope for, that I think that may be one of the reasons why many people think that Uhuru made all these discoveries. The paper, Cenex 3, was submitted 2 weeks after the Webster and Murdin paper had already appeared in print in Nature, but it was not even referenced in the Uhuru paper. And I think the reason is not that they purposely avoided it, but I think these guys were so busy and so excited about Cenex 3 that they hadn't even read Nature. That's my explanation. However, if they had referenced that paper of Webster and Murdin, history might have evolved differently. I would like to show you the pulsations of Cenex 3, which are absolutely fantastic. So the separation between the peaks is the 4.8 seconds, which is the rotation of the neutron star. Don't pay attention to this shape, because that's the result of the collimation of Uhuru. And then I also want to show you the eclipses. When the neutron star hides behind the donor, you see that here. With a little bit of imagination, when there is data, then you see very dark lines here, and then all of a sudden, nothing, and then back again. And during that nothing, the star is hiding, the neutron star is hiding behind the donor. And the period between these troughs is 2.1 days, which was exactly the same period that they found from the Doppler shift of the rotating neutron star. When the optical identification of Cenex 3 was found, the mass could be determined of the accretor, and it turned out to be a neutron star. That was obvious because of the 4.8 seconds. Cygnus X1 never had pulsations, because Cygnus X1 is a black hole, and a black hole has no surface, so you can't get pulsations. But if you see 4.8 second pulsations, you know it's a neutron star. So that was not a big surprise. In 1972, Uhuru paper, Gursky was first author, had conclusive evidence of extended emission from the Virgo cluster, the Coma cluster, and the Perseus cluster. This was hot gas that was trapped in the potential well of the cluster. And it was so hot that it emitted X-rays. And the mass of that hot gas, as the student remembered, was many times the mass of the galaxies, and that has consequences for cosmology. There have been several Uhuru catalogs. The last one was the 4U catalog in 1978. The two first authors were Bill Foreman and Christine Jones, and the catalog had 339 sources. And a typical error box for the source was 2/10 of a square degree. And I remember I was with Herb Gursky at a conference, and someone asked Herb, how come that optical counterparts optical lie outside the Uhuru error regions. And then Herb answers, that's because the area outside is way larger than the area inside. I want to show you the Uhuru catalog results. The fatter the dot, the stronger the source. Galactic coordinates, you see here. And if for those of you who are nearby, they can see here's CoX1. You will probably see Cygnus X1 right here. And Sen X3 is also marked, is here. If we compare the situation from 1962, from the early days, the early 60s, with the situation now, and I'm particularly thinking of the Chandra Observatory, then the sensitivity of detecting a source is now 10 million times higher than it was in the early days. 10 million. And the angular resolution is 1 billion times higher today than it was. I will show you here a nice slide that was given to me by Fred Baganov. This is 8 by 8 arc minutes made with Chandra Observatory. And you see here 1,000 X-ray sources. None of these sources could ever have been seen in the 60s, not only because of the sensitivity, but keep in mind that the resolution in the 60s was of the order of a square degree, and a square degree is 20 times larger than the size of this screen. So none of this, what you see here, could possibly ever have been seen. A thesis was written by Hirsch on the history of X-ray astronomy, and they listed the names of people who in that decade had more than 13 publications on X-ray astronomy. And I surely don't want you to read all the names, but since this is MIT, I underlined the people at MIT to show you that MIT was extremely active in the early days. So, Bill Smith, Gordon Garmeyer was at MIT, so he had 16 papers in that decade. Srikantan was at MIT. Sal Rappaport was at MIT. George Clark, with whom I worked. Hale Brott, sitting right here. Hale had 23 papers. Or did he have 22? Well, if he had 22, I had 23. Here, Minoru Ode and Harvey Tannenbaum, although most of his papers were from his days with Ricardo, but Harvey was a graduate student here at MIT. 50 years ago was the birthday of X-ray astronomy. And 10 years ago, Riccardo Giacconi received the Nobel Prize for physics. And it was cited, we can read that together, the pioneering contributions to astrophysics which have led to the discovery of X-ray sources. There is no question that Ricardo deserved the Nobel Prize. But in my opinion, it would have been so nice and appropriate if already 25 years ago, the Nobel Prize had been awarded to Ricardo, to Bruno Rossi, and to Herb Friedman. Bruno died in 1993. Herb Friedman died in 2000. Clearly, the Nobel Committee was too slow. Thank you.
Thank you, Walter, for sharing this personal history of the development of a subject of physics on this very fitting day, the day in which the 2012 Nobel Prize in Physics was awarded. And to see the contributions made by so many here at MIT and in the area, AS&E and Harvard-Smithsonian, really is a testament to what we're celebrating today in the astronomical event. That is, the importance that one institution and a group of dedicated scientists can make to the establishment of a new field. So with that, I open the floor to questions from the audience. I'm sure there will be some, and I invite you to come to the microphones. And George Clark indeed is here, the hero of much of this work beneath it.
People are dumbfounded.
Okay.
Bernie, I knew you would be the first. It fits your personality.
From an embarrassing silence. This is rare. I just wanted to comment that with the exception of SCOEX 1, which was a really...
A little louder if you can, because I have a hearing disability.
So do I.
Oh, we both have one, that's right.
I can hear myself talk. But one should note that a great deal of the work was foreshadowed by discoveries in radio astronomy.
I can't follow your argument. Maybe without the microphone it may be better.
Was that you radio astronomers had our role to play, mostly because we both dealt with high energy phenomena. And in particular, the Crab Nebula, which is one of the most dramatic, was a radio discovery. And the detection of the pulsar at the center of the Crab Nebula was also a radio discovery.
SIBO.
No.
No, the pulsar was Dave Stalin, but the period was determined in Arecibo.
That's correct. Dave Stalin and...
But Dave Stalin found it, yeah.
But Arecibo, again, they shortened the integration time. And
well, they knew there was a pulsar, and so they got the period. Yeah. So what is your point now? I miss it.
we'll have a comment.
Oh, well. Thank you for the comment.
I didn't want Dave Stalin to get a little bit of credit.
I gave Dave enough credit, I hope.
He mentioned it, but he didn't mention that it was radio.
Yeah, you didn't say.
Pulsar. There were only radio pulsars in those days. 1967, the Cambridge group discovered 3 pulsars. They first thought actually it was intelligent life somewhere else, and they called them little green men. You know that story. And then finally they realized it wasn't the little green men. When they published it, they did not realize that what they were looking at was rotating neutron stars. It was Tommy Gold from Cornell who immediately said, there's got to be neutron stars rotating because of the incredible accuracy in the period. It was Zwicky.
The deceleration of the period.
It was Zwicky and Bade, who in 1934, only 2 years after the discovery of a neutron, casually suggested maybe neutron stars exist, and maybe they are formed in supernovae. Amazing, what an insight. So Stalin, who knew that, immediately looked at the Crab Nebula to confirm Zwicky and Bade, and he found the pulsar. But he didn't have the sensitivity to get the period right, and so when Arecibo heard that, they found it 33 milliseconds. I just made a comment, it's not a question.
I can see that we're going to have a lot more history to recount, but let's have some more questions from the audience. Neil.
Walter, you launched numerous balloons. What was your betting average? terms of ones that were successful and ones that you lost?
I would say over the years, the beginning, George and I did. George actually deserves the credit for having been the first person in 1964. I was not at MIT to fly a balloon and discovered high energy X-rays from the Crab Nebula. And what is even interesting historically, which you can read about in my book, For the Love of Physics, originally he wanted to look during the day at SCO X-1. The moment that he heard that Friedman had identified the Crab Nebula, he changed his plans and he went for a night flight and discovered X-rays from Crab. When I joined George's group, I got involved in the ballooning. Well, and George was very generous to me. At one point he said, why don't you take the group? I would say the total number of balloons that I have flown is probably 25, and the success rate was probably not much higher than 60 or 70%. However, our instruments always worked. And that's largely due to George Ricker.
Not you.
And our competition, who also had a record on balloon failures, they also had about 70% success of the balloons. They didn't even have 50% success on their instruments because their batteries froze up. All kinds of nasty things. So at least every time that we made it to altitude, we went up to 145,000 feet. 145,000 feet. Airplanes fly at 30,000 feet. Our instruments always worked. George was there when GX1+4 was discovered.
Walter, what you don't know is I taught George physics.
That was after you watched my lectures on the web?
No, sir. He's in my fraternity. I was a junior when he was a freshman, and he needed help.
Oh. So you deserve credit for GX1+4.
And a lot more. Walter, I have a question about the role of theoreticians. Several times in your talk, the word black hole rolled off the tip of your tongue as if it was the most natural thing in the world. But there were a few skeptics at that time, and maybe even still are, about the existence of these creatures in space. When did you become convinced that some of these cosmic X-ray sources were in fact black holes?
All right. For this talk, I was only allowed 60 minutes. And therefore, there's certain things that you have to leave out. Before the discovery that Cygnus X1 was very likely a black hole, it was already generally accepted that the extragalactic sources, the very bright radio and X-ray sources, that they were already supermassive black holes. M87 has a black hole of the order of 1 billion solar masses. That was already pretty much accepted. The discovery of the black hole in Cygnus X1 was the first stellar mass black hole. We now know very accurately what the mass is, largely due to one of my former graduate students, Jeffrey McClintock, who, strangely enough, is not here. We now know that the black hole is 15 solar masses. Now coming back to your question. When did I really believe that it was a black hole? Yeah, that's a slow process, you see. When the pulsations were seen from all...
Maybe you don't believe it now.
Oh, there's no doubt in my mind. I'll bet you a year's salary. Your salary against my salary. Absolutely.
Didn't I give you a raise recently?
No, there's no doubt. See, the interesting thing is that the method that was introduced by Webster and Murdin and by Bolton, that you can get the lower limit of the accretor, has been done now dozens of times on many transient sources. And every time that you find that the mass is more than 3 solar masses, no pulsations. And every time that you find that the mass is below 3 solar masses, pulsations. Why do you think that is? Because black holes cannot pulse because they have no surface. So it's obvious. For me, it's not even an issue. I doubt whether there's any astronomer in the audience, any prominent astronomer, I should say. I doubt whether there is anyone who doesn't believe that many of the X-ray binaries are, the transients particularly, have a black hole as an accretor. If you have the courage to stand up, do it! I knew it.
Yes.
Have I convinced you?
You have. Yes.
Thanks. You mentioned optical observation. I just wonder, as an astronomer, if you have any instinctive preference for any one form of observation versus another.
What is the question?
Do you have any preference for one form of observation or wavelength band, X-rays, optical, radio, for studying these sources?
Absolutely not. Anything that would add to our knowledge, so much the better. No, in fact, a major discovery, which, again, I have only 60 minutes today. The whole story about when I casually said the most likely optical identification of Cygnus X1. I could tell you 10 minutes how that came about. That's a beautiful story. Many groups with rockets tried to pinpoint that source. And the error boxes became smaller and smaller and smaller and smaller. But they were always too large to be lucky and find an optical counterpart. And then one day, that was actually on the APJ letters that I showed you, then one day, Yelming discovered radio emission from a source in the general direction of Cygnus X1. And that was extremely unusual. Since he then suggested, well, there's got to be Cygnus X1, the error box, all of a sudden, because of the accuracy of the radio positions, all of a sudden became 4 arc seconds. And in those 4 arc second box was a B0 supergiant. That was obviously the optical counterpart. And so then, what Webster and Murdin and Bolton looked at that B0 supergiant. What is even more interesting, which I had to leave out because I only had 60 minutes, the great astronomer Alan Sandwich looked at that star and published and said, this is an ordinary B0 supergiant. There's nothing special about it. This is not Cygnus X1. The great Alan Sandwich. But the other guys looked a little longer and they found that it was a binary. So even something as, casually saying the most likely optical identification, there's a whole history behind that. And it was only because of the radio detections that the error box from this big all of a sudden became this small.
Thank you.
Sorry when I get a little bit emotional, but it's part of my nature.
We've learned a few lessons from this talk. One is that it pays to make careful measurements. Of course, you help yourself by coming up to bat multiple times so that you have the chances to make those measurements succeed. And finally, I think there's no better company to share the discovery and the excitement of physics and astrophysics than with Professor Walter Lewin. And I'd like to invite the audience now to come to a reception down in Lobby 10, one floor below us, to have the chance to speak with Professor Lewin and with each other. Thank you very much for coming to this colloquium.